at the end of the session. So yeah, as you can see, we're going to talk about permutations and combinations today. So we'll cover the basics today, and then we'll go into more advanced topics in the next session, in next week, that is. So I'm sure that some of you are already familiar with the concept of permutation and combination and how it's applied in problem solving, but still we'll go over it anyway, assuming that some of you don't know about it as much. So permutation, first we'll tackle permutation. So what is a permutation? Permutation is an ordered arrangement of a selection of elements, all right? So an ordered arrangement, that is the key word here, okay? So you select some elements and an ordered arrangement of that element would be a permutation. So every possible ordered arrangement of a certain selection of elements would give you different permutations, okay? So when we're talking about permutation, it's a selection of distinct objects, all right? It's a selection of distinct objects from a choice of distinct objects, and in that selection, order matters. Order matters, okay? So if you're trying to count the total number of permutations by selecting R elements from a choice of n distinct elements, we represent that by the term P and R. P and R in this way. P and then parentheses, and inside you have NR. So you have a set with total number of n distinct elements, and from that you're counting R permutations. And what is R permutation? What is an R permutation? An ordered arrangement of R elements, R distinct elements from a set. All right, an ordered arrangement of R distinct elements of a set is R permutation. And every new arrangement that you make among these R elements would give you a new permutation. All right, so all R permutations, all possible R permutations from a set that contains n distinct elements, that would be denoted in this manner, P and R. So we are counting R permutations from a set that contains n distinct objects. Okay, so on to how is it that we calculate this. First of all, before that, we represent this in this way, in this manner, or in either one of these ways, all right? With R as a subscript and N as a superscript, or in any of the other two manners. All of these symbols represent permutation of R elements from a choice of n distinct elements. Okay, how do we calculate that? We use this formula for calculating that, all right? N factorial by n minus R factorial. This is what we use. What is n factorial, guys?
N into n minus 1 into n minus 2 and so on.
And so on until 1.
Until 1.
Exactly. Very good. And what is n minus R factorial?
N minus R into n minus R minus 1 into এইভাবে যেতে থাকবে 1 পর্যন্ত.
That is correct. So if you calculate this, what you get? You would cancel out all the elements that you get from n minus R factorial. You'd cancel that from the n factorial value, right? N factorial থেকে all the values that you have under n minus R factorial as well, they would get cancelled out. So ultimately, the result we would get would be equivalent to this. N multiplied by n minus 1 multiplied with n minus 2 multiplied with n minus 3 and so on until n minus R plus 1. This is what we would get. The rest of them from the n factorial, the rest of the factors in the product in n factorial would get cancelled out because of n minus R factorial. So this is what we get. N multiplied by n minus 1 multiplied by n minus 2 and so on until n minus R plus 1 based on this formula. Is that clear? Is that bit understandable?
I didn't understand which one gets cancelled.
Come again?
The one you said, miss, it gets cancelled, something like that. I didn't understand.
Yeah, so think about it. So in your when you're calculating the factorial of n, okay, factorial of n, when you're calculating that, it's n multiplied with n minus 1 multiplied with n minus 2 multiplied with n minus 3 and so on until n. So between this entire range, within this entire range, starting from n and then decreasing until 1, the entire product. Here, somewhere in among these factors, you would also find the factors that you find in n minus r factorial, right?
Yes, miss.
So think about it. Let's say n is 6 and r is 3. So here you'd have 6 factorial, and what would you have here? 3 factorial. 6 factorial এ what you would have as factor, ওই factorগুলো থেকে কি 3 factorial এর factorগুলো কি বাদ যাবে না because of this division? That's what I'm saying. So if you get rid of them, then what do you have in the end? What do you have as the result? N multiplied by n minus 1 multiplied by n minus 2, and so on until n minus r plus 1. Until n minus r plus 1. All right?
Yes, miss.
So does it make sense now that this will be equivalent to this?
Yes.
Guys, does it make sense to everybody that this formula equates to this formula?
Yes, ma'am. Yes, ma'am.
Okay. Now, how do we get here from permutation? We understand that these two are equivalent, fine. But how do we get to this series? N into n minus 1 multiplied by n minus 2, and so on until n minus r plus 1. How do we get here from permutation? To figure out that, think about what we do when we calculate our permutations from n distinct objects. How do we do that? First of all, r and n, both of them are positive integers where r will never be greater than n. That is the condition. If that condition is satisfied, in that case, counting our permutations from n distinct objects, this process can be broken down into smaller tasks. How many tasks? R number of tasks. Think about it. When you are counting R permutations, what is it that you're doing? You are selecting an object for each of the positions, right? And how many positions do we have to fill up? R positions, okay? So when we are doing this, R permutations from n distinct elements, what we are doing is you can imagine that we have R positions, and we have to fill up each of these positions with what? With elements from the set that contains n objects. Does it make sense? P and R. So the process of counting R permutation is what basically? It's basically choosing an element for each of the position among the R positions. That is choosing each of the elements. So when you're counting R permutations from n objects, you are actually choosing R elements, right? From n objects. You're choosing R elements from n objects and rearranging them in different order. You're choosing R elements from n object and rearranging them in each order. So if we divide up this entire procedure into the task of choosing each element, how many tasks will we have? R number of tasks. The first task is what? Choosing the first element. The first task is choosing the first element in the first position. The first element in the first position, choosing the element for the first position, that is the first task. Now for the first position, how many options do we have to choose from? We have total n elements in the set. So how many options do we have in order to choose the element for the first position?
N options.
N
N
options.
options. Exactly, correct. So there are n ways basically to do the first task. All right, so moving on. For the second task, what is the second task? Choosing an element in the second position. So when you get to the second position, by then you have already selected an element for the first position, right? Whichever one you select, doesn't matter. Regardless of that, you already selected an element for the first position, yeah?
Yes, ma'am.
So do you have n elements, n options left anymore?
No,
You
miss.
still
No.
have n choices? No. Remember, it has to be distinct. Remember, it's distinct. So once you're done with choosing the element for the first position, you have n minus options to choose from in order to choose the element for the second position. Similarly, for the third position, by the time you get to the third position, you have already selected 2 elements. By the time you get to the third position, you have already selected 2 elements. So for the third position, you have n minus 2 options left to choose from. That is, to do the third task, there are n minus 2 ways. Similarly, to choose the fourth element, in the fourth position, you have n minus 3 options to choose from. All right. For the fifth element, how many options do we have to choose from for the fifth position? How many options do we have for the fifth one?
N
N minus 4.
N minus 4, exactly. Why? Because by the time you get to the fifth position, you've already selected 4 elements. So you have N minus 4 options left to select the element for the fifth position. And it will keep progressing in that way. All right. Same goes on until the rth position, the element in the rth position. That is the last element, the rth element, selecting the rth element, the element in the last position. To select that one, how many options do we have? By the time you get to the rth position, how many elements have you chosen so far, guys? When you're choosing the rth element, before the rth element, how many elements have you chosen? R minus 1, right? Does it make sense?
Yes, ma'am.
When we get to the rth position, by then we have already selected R minus 1 elements. We have already selected elements for R minus 1 positions. So how many options now will we have left for selecting an element for the rth position? We have already selected R minus elements by the time we got to R. We've selected this many elements already. And the total number of elements in the set is n. So the number of options left to choose the rth element position is n minus R minus 1. That is, if you calculate it, distribute the negatives, then you get n minus R plus 1. So there are n minus R plus 1 options left to choose an element for the rth position. Okay, is that clear? For the element in the first position, there are n ways to choose the element for the first position. That is, there are n ways to do the first task. For the second task, which is choosing the element in the second position, there are n minus 1 options. That is, there are n minus 1 ways to do the second task. Similarly, there are n minus 2 ways to do the third task, n minus 3 ways to do the fourth task, and so on until the rth task, which is choosing an element for the rth position, and this task can be done in n minus R plus 1 ways. Until this much, is it clear with everyone?
Yes, ma'am.
Yes, ma'am.
All right, very good. If that's clear, next, first of all, we had an entire procedure. We broke it down to smaller tasks, all right? And we found out each of these tasks can be performed in how many ways. Now notice that in permutation, order matters, right? Since order matters in permutation, because of that reason, for every possible choice of the first element, you have a number of choice for the second element. For every possible choice of the second element, you have a number of choice for the third element. All right? So it's all relevant. That is, there are n ways to do the first task, n ways to choose the first element. And for each of these ways, for each of these choices, for every single one of these choices, you have n minus options to choose the second element. That is n minus ways to do the second task. And for each and every one of those n minus options to choose the second element, you have n minus 2 options to do the third task. All right? So hence, we can say that we can apply the product rule here because order matters. And because of that, we can say that regardless of the choice that you make, for every single one of the n choices for the first element, you have n minus 1. For the second one, for every single one of the n minus 1 choices, there are n minus 2 ways to choose the third element, and so on. Because of that reason, we can apply the product rule here. So if we apply the product rule, what do we get? N multiplied by n minus 1 multiplied by n minus 2 multiplied by n minus 3, and so on until n minus R plus 1. So it will be the product of all the different sets of ways to do each of these tasks. All right? Counting R permutations from a set that contains n distinct objects. Okay? So by applying the product rule and by analyzing what permutation means by definition, we get to this point, that counting R permutations from n distinct objects would be equivalent to this. Is this clear with everyone?
Yes, ma'am.
Any questions or confusions left, guys? Do you guys understand how we broke down the procedure, and why we applied why we could apply the product rule here. Is that clear, guys? So no
Yes,
question.
kind of.
Kind of. If you
Yeah.
have any question or confusion, you can go ahead and ask. All right.
Miss, can you tell me the art position can be filled in n minus r minus 1? This
This
one?
part.
Yes.
This part.
Yes.
In order to understand that, understand what's happening before this. Do you understand that for the first position, you have n options? Do you understand that? Fine.
Yes, miss. Yes, miss.
Okay. So once you have selected the element for the first position, then you move on to the second position, right?
Yes.
So when you choose, when you're trying to look for the options to choose the second element, how many options do you have left? Remember that you've already selected one element, right? You've
Yes.
already selected one element. So do you still have n options left to choose the second element?
No, miss.
No, we have n minus 1 options. When you get to the third element, third position, when you get to the third position, how many elements have you already selected?
2.
2. So how many options do you have
N
to
minus 2.
select the third? N minus 2, exactly. So understand this format, okay? So whenever you choose an element for a certain position, how many options do you have left? N minus the elements that you have already chosen, right?
Yes, miss.
N minus the number of elements you have already chosen. So when we get to the rth element, when we get to the rth position element যখন choose করব, by then how many elements have we chosen?
R
We've
minus
already chosen r minus 1 elements, right? Because r is in the last position. So
Yes.
you've already, and if you're going to the rth position, you've already selected r minus 1 elements. Is that clear?
Yes, miss.
So in total, there are n options. R minus 1 elements have already been chosen. So how many options do you have left?
N
N
minus
minus r minus 1, as simple as that. So that gives us what? N minus r plus 1, this one. This is
Yes.
equivalent to this, right? So you have n minus r plus 1 options to choose the element in the rth position. Okay. And since order matters here, that's why we can also say that for every one of the choices, every one of the n choices, for every one of the n choices, for the first position, we have n minus 1. What do I mean by that? N number of options. Whichever you select, for each one of the choice, you have n minus ways to select the second element, right?
Yes, miss.
So because of that relation, we can apply the product rule here as well. Is that clear now, Fahim?
Yes, miss. Understand. Thank you.
Okay. Anybody else has any confusion regarding this proof? Any questions or confusion, guys?
No, miss.
Okay. Cool. All right. Okay, then let's apply the idea of permutation here. The solution will look very simple and straightforward to you. I'm sure of that. But please focus on the method of identifying the fact that we have to solve this problem by applying permutation. Because in the exam, obviously, you're not going to be told that you have to apply permutation. You have to read the problem and then figure out that, okay, we have to apply permutation here. All right? So let's go over the problem first. So there are 100 different people, and among these 100 different people, we have to select a first prize winner, a second prize winner, and a third prize winner. Okay? How many ways are there to select the winners, the 3 winners from these 100 different people? Okay. So how do we know that permutation is applicable here? First of all, we have 100 distinct objects. Why distinct? Because these are people. So 100 different people. So we have 100 distinct objects, and from there, we have to select 3 distinct objects again, right? 3 different people. From 100 different people, we have to select 3 different people. So 100 distinct objects, and from there, we have to select 3 distinct objects. Okay, that part. And then the more important part, when you select 3 distinct people, when you select these 3 different people, what are you selecting them for? You're selecting them specifically for a first prize winner, a second prize winner, a third prize winner. So the order in which you select them matters. That is, which, even if it's the same 3 people, even if it's the same 3 people, which specific person you select for the first prize, which specific person you select for the second prize, and which one for the third prize, that is important, right? So if I say that there is a quiz competition or something like that among you guys, and if I say that Fahad wins the first position and Jarif wins the second position and Fahim wins the third position, okay? If I say that, that's one selection. Then if I say that, okay, wait, I made a mistake. The third position is not taken by Fahim. The third position goes to Fatima, okay? Let's say Fahad won the first position, Jarif won the second position, and Fatima won the third position. This is definitely a different outcome, right? Because this is a different selection, right, guys?
Yes,
Are
miss.
the two outcomes the same?
No.
No, it's
No.
different.
Because they are completely different selection. The important point here is that even within the same selection, if you change the order, then it's a different outcome. So in the current selection, Fahad came first, Jarif came second, and Fatima came third, right? So Fahad goes back home and says that he came first, his parents are happy. And then I tell you that, oh no, I made another mistake. Jarif is the one who came first, Fahad came second, all right? If I do that, is that the same outcome for Fahad and Jarif?
No, miss.
No, it will change.
Yes, exactly. So see, we have the same selection. It's still the same 3 people. It's the same 3 people, but who the prize goes to matters, all right? That is, if the first prize, second prize, third prize, which person gets what prize? If we reshuffle that order, if we reshuffle that arrangement, we get a different outcome, right? So what does that tell us? It tells us that not only do we have to select 3 people, also among these 3 people, which person gets first prize, which person gets second prize, which person gets third prize is also important. That is, among these 3 people, a different arrangement would give us a different outcome. And the definition of permutation fits this exact criteria. Yeah? Because in permutation, not only do you have to select a certain number of objects, and among those objects, different order or different arrangement gives us new permutation. So that is why, based on that, you should be able to tell that this problem fits the description definition of permutation. Okay, so this is basically counting 3 permutations from 100 distinct objects. That is, the value of R here is 3, the value of N here is 100. So P and R is P103 or 100P3. Okay, and it is equivalent to 100 multiplied by 99 multiplied by 98. It makes sense with the formula, because 100 factorial divided by 3 factorial is what? From 100 factorial, 100 factorial divided by 97 factorial. 100 factorial divided by 97 factorial. 100 factorial divided by 100 minus 3, 97 factorial gives you what? You cancel out all the factors that you have in the 97 factorial, all right? From the 100 factorial. So you're left with only 100, 99, and 98. So 100 multiplied by 99 multiplied by 98. From that perspective, it makes sense. Also, if you think about the product rule, even there it makes sense. For the first prize, when you're trying to select someone for the first prize, how many options do you have to choose from? 100.
100.
Yes. So once you've selected the first prize winner, you move on to the second prize winner. But when you move on to the second prize winner, you've already selected one person as the first prize winner. So now you have 99 options left. Similarly, for the third prize, since you've already selected 2 people prior to selecting the third prize winner, you've already selected 2 people, you have 98 options left. All right. And since order matters, since for every one of the choice of 100 people, you have 99 choices for the second prize, and for every one of the choice of these 99 people, you have 98 options for the third prize. All right. So the product rule is applicable here, 100 multiplied by 99 multiplied by 98. Makes sense, guys?
Yes, ma'am.
Yes, miss.
Okay, cool. Okay, let's do another problem then. Here we are asked to count all possible permutations. Previously, we were asked to count 3 permutations. That is NP3, where N is equal to 100, 3, and R is equal to 3. All right. Here, in this problem, we are asked to count all possible permutations of the letters A, B, C, D, E, F, G, H, where every single permutation must contain the string ABC. String ABC mane ki? Think about programming. Is the string ABC the same as the string BAC?
No, miss. Order nahi.
No, it's not the same, all right? So ABC, the string, if it must be there in every permutation, what does it mean? Every single permutation must have these letters together and in this specific order. These three letters must be there together and in this specific order. That is ABC, then D, E, F, G, H. That is one possible permutation. Another possible permutation is what? D, then ABC, then E, F, G, H. Another is what? D, E, then ABC, then F, G, H. Okay. So here, basically, what are we doing? Notice, aren't we treating ABC as one single object? Aren't we just treating ABC as one single object?
Yes, miss. Because
Think about it. Yeah, go ahead.
Yes, miss. It's string confidence also, so we can consider it as a single object.
Yes. It must be there in all permutations as a string. So you can just say that ABC is one single object. Together, ABC is just one single object. So we have ABC, 1, then D, then E, then F, G, H. So how many objects do we have actually here in total? 6 objects. Even though in the first glance, it looks like there are 8 elements here. Even though in the first glance, it looks like there are 8 elements here, but actually we have 6 elements because you can consider ABC together as one single element. Because ultimately ABC has to be together as a string. So the order within ABC doesn't matter and you cannot even split them up. So it's just one element. You can just consider ABC as one element and the rest of the 5 elements together, you have in total 6 elements. So basically, you have 6 elements here and you have to be 6 distinct elements here, by the way. All of them are different from each other. So 6 distinct elements here. And you have to count all possible permutations for these 6 elements, okay? All possible permutations, okay? So if we have to count all possible permutations, so that is equivalent to P66, all possible permutations, right? So we have a choice of 6 elements. From there, we are also choosing 6 elements where order matters, okay? So it's P66, which is equivalent to 6 factorial. Does it make sense, guys?
Yes, ma'am.
yes, miss.
All right. What if you were asked to count 3 permutations for the same problem? Instead of counting all possible permutations, you were asked to count, if you were asked how many 3 permutations of the letters A, B, C, D, E, F, G, H contain the string ABC?
Miss 6,3.
P63 or 6P3, right?
Yes.
Very good. Exactly. So counting 3 permutations means what? Basically, you have to count the permutations, count all possible permutations, count all possible permutations with 3 letters among these letters where every permutation must contain the string ABC. Right? So yeah, that.
Miss, I didn't understand what you said right now. 3 letters.
So I mean here, why do we have P66? Because how many permutations? That is how many? I mean, that is we have to count all possible permutations. Why do we have P66 here? Because they asked simply how many permutations. That is count all possible permutations. So that's why we have P66. What if instead of this, they ask you to count the number of permutations with only 3 letters? Similarly, for example, here, why do we have P103? Why? Because from 100 distinct options, you are selecting only 3 distinct options and rearranging them to count the permutation, right? Why is it P103? Because from 100 distinct options, you're counting the permutations for only 3 choices, all right? Only 3 choices. You have to make only 3 choices here. However, here, you're asked to count all possible permutations. So you have 6 distinct objects, and from there you have to choose 6 objects, okay, and rearrange them. That's why we have P66. However, if the number was lower, I mean, like I'm telling you the distinction between counting all possible permutations, the distinction between counting all possible permutations and counting a specific number of permutations. Here you're counting 3 permutations. You're counting a specific number of permutations among 100 distinct objects. Remember the term R permutation? R permutation. What is R permutation? Ordered arrangement of R elements. And we are counting when we are doing PNR. When we are doing PNR, what are we doing? We are counting R permutations, the total number. We're counting the total number of R permutations from N objects, right? So here, P103, you're counting total 3 permutations from 100 different objects. However, here, they ask for all possible permutations. Okay, so that's why it's P66. That's just that distinction. I wanted to make sure you understand that. The distinction between counting all possible permutations and the distinction and counting a specific number of permutations. Is that clear?
Yes, ma'am.
Counting 3 permutations versus counting all possible permutations.
Yes, miss.
Okay. So in that case, let's move on to combination. So first of all, how do we define combination? I will define combination with respect to permutation. I think that it will be clearer that way. So if you understand permutation, then the only distinction between permutation and combination is that in case of combination, order doesn't matter. Order does not matter for combination. In case of permutation, what is it that we were doing? We were choosing R distinct elements, and then we were rearranging the R elements every time. For every choice of R elements, we were also counting all the different arrangements. That is, changing the order, we could come up with a new permutation. However, in combination, order does not matter. That is, you just simply come up with all possible selections of R choices, and that's it. You do not rearrange them, because even if you rearrange the order, it will not give you a new combination. If you select a fixed R distinct elements, then reshuffling within those elements will not give you a new combination. Okay? So when it comes to combination, it is just simply selection. It is just simply selection. In case of permutation, even if they say the word select here, because of first prize winner, second prize winner, third prize winner, because of this distinct position, we can say that the order matters here. So not only did we have to select 3 people, among them we also had to designate who gets first prize, who gets second prize, who gets third prize. So the selection, you select first and then you rearrange, and that's how you count the permutations. In combination, the rearrangement part doesn't matter, order doesn't matter. So an R combination of elements of a set would be an unordered selection of R distinct elements of the set. So it's just selecting R elements, that's all, right? Order doesn't matter. So counting total of R, counting the total number of R combinations from a set that contains N distinct elements, you represent that with CNR in this format, CNR. Or this way, this way, this way. The most common one that we will use in this course is this way of representing it, either CNR or this one. We will mostly use either this representation or this one, okay? So N on top, R at the bottom, and then surrounded by parentheses. So any one of these notations should tell you that it's for combination from N to R, NCR. Okay. Now moving on to how to calculate NCR. So NCR or CNR can be calculated using this formula: N factorial divided by N minus R factorial multiplied by R factorial. It is represented in this way or this way, yeah, but the way of calculating it is N factorial by N minus R factorial multiplied by R factorial. Yeah. Okay, so this is the formula that we use. Fine, but how? How do we get to this formula? How does it make sense that we use this formula for counting the combinations? Counting our combinations from N distinct objects. Given that R and N, both of them are non-negative integers, and R will never be greater than n. That is, r will always be less than or equal to n. We can always go by this formula. For r equals to 0, this formula obviously makes sense. If r is equal to 0, we have n factorial divided by n factorial, right? If r is equal to 0, we have n factorial divided by n factorial. And what does that give us? 1. The result is 1. If r is equal to 0, if you have to choose 0 elements, then what do you get? Only one result, null. Right? Nothing. So the result makes sense when r is equal to 0. The formula is true when r is equal to 0. Now, moving on to the formula when r and n are positive integers. Okay? If they're positive integers, in that case, how does it make sense that we get this formula? Think about it. First, think about the definition of permutation. When we are doing permutation, what are we doing? First, we are selecting r number of objects from a choice of n elements, and then we are changing the order within those r objects, right? Here, for example, what are you doing? You have 100 different people, 100 different options to choose from. From there, you can select any 3 people. So first you make the selection, right? First thing we are doing is we are making the selection. You can choose any 3 people, and then you designate the position. Which person gets the first prize, which the second, which the third. And then if you change the order, that's a new outcome. Every time you change the order within these 3 people, you get a new outcome. So basically, for counting the permutation, you can break it up into 2 tasks, where the first task is choosing the elements, selecting the elements. And then the second task is changing the order within that selection to come up with new permutations. Right? Does it make sense, guys? The fact that we can break the process of permutation down into these 2 tasks.
Ma'am, could you repeat? I zoned out.
Yeah, surely. So permutation by definition is what? Permutation is ordered arrangement of a couple of distinct objects, right? So when you count permutation, if we think about the process of counting permutation, how do we do that? First, we select R objects, right? P and R. When you're trying to count all P and R, that is all R permutations from n distinct objects. What are you doing? Can we not break this procedure down into 2 tasks, where the first task is selecting the R elements from the n options and then reshuffling among these R elements to come up with new permutations? Can we not break it down into 2 tasks like that? First task is choosing R elements. We have n options in total. A total n object theke we will select R number of objects. And once we are done selecting the R objects, within these R objects, every time we change the order, we get a new permutation, right?
Yes, ma'am.
Yes, miss.
Does that make sense? If that is the case, if we can do that, then the procedure can be broken down into 2 tasks, basically. 2 tasks. First, selecting R objects, and then within those R selections, within those R number of selections, changing the order every time to get a new permutation. So basically, if you have a task of P and R, the first task, which is selecting the R elements, selecting just simple selection, without thinking about order at all, without thinking about rearranging or anything like that, just the first task is what? Just simply selecting R elements. Just simply selecting R elements. This simple selection of R objects from n possible objects can be done in how many ways? C and R ways. Because the simple task of selecting R objects from n objects is actually the definition of combination, right? In combination, we just make a simple selection. And we don't worry about order, because order doesn't matter in combination. So here, if you think about permutation and you break it down into 2 tasks, the first task is selecting the R objects. And in how many ways can you select R objects? And just simply select R objects in C and R ways. Is this clear with everyone? That the first task can be done in C and R ways?
Yes, ma'am.
Okay. Then what is the second task? The second task, once you have selected R number of elements, once you have selected these R elements, the second task is counting all possible arrangements within these R elements. That is, you keep changing the order within these R selections and you count all possible distinct arrangements. Okay? Every single new order, you count it as a new permutation. So basically, you have already selected R elements. Among those R elements, you're counting all the possible different arrangements within these R elements. Within these same R elements, you're counting all possible different arrangements. So what are you doing here? PRR. So the second task, which is reshuffling among the selection, can be done in PRR ways. Does that part make sense? That the second task can be done in PRR ways.
Yes, ma'am.
Miss, can you explain it again, please? The second
The
task.
second task. Okay.
Yes.
For that, think about what we're doing here. So what is the first task? First task is selecting 3 different people. All right. First task is selecting 3 different people. So the first task can be done in 100C3 ways. Does that make sense?
Yes, Miss.
Okay. The second task is what? Once you have selected the 3 people, the second task is counting all the different possible arrangements within these 3 people, right? Let's say I select 3 people. You, Fahim, Jarif, and Fatima for the price. Fatima, Jarif, and Fahim, these 3 are my selections. Is that all? Is that just one permutation that we can get from this selection? No. From the same selection, once we have made the selection, here we can get other permutations as well. What are those permutations? Rearranging within this selection and shuffling the designation of the first price, second price, third price. All right. Every time I change the order of which person gets which price specifically among the same 3 people, I get a new permutation, right?
Yes, Miss.
So you're selecting 3 people, and within those 3 people, you're counting all possible arrangements, all possible order arrangements among these 3 people again, right?
Yes.
So first you're doing 100C3, and then within these 3 people, you're counting every single possible arrangement. So then you're doing P33. Okay. Once you have selected 3 people, you only have these 3 people, right? You have already made the selection. You only have these 3 people. Then you have to count all the permutations within these 3 people. All right. So 100P3. So 100C3, and then the second task, 100P3. Is that a bit clearer, Fahim?
Yes, Miss.
Okay. All right. So if you understand that, think about the generic case. If we have to count our permutations from n distinct objects, first of all, it can be done by selecting the R objects, and the R objects can be selected in C and R ways. And then once you have selected the R objects, within those you count all possible different arrangements within these R objects, and that can be done in PRR ways. Now is it clear?
Yes, Miss.
Okay. So, and also remember that for every one of these ways to select R objects, for every single one of these choices, you have PRR options. Okay. So let's say selecting, so we went with the selection of Fahim, Jarif, and Fatima, right? And for this selection, we counted all different possible permutations, that is all different ordered arrangements. For a different selection, let's say I go with Nafisa, Jarif, and Fahim. For that selection, Nafisa, Jarif, and Fahim, how many permutations are there within this selection? Again, P33, right? For a different selection. If I go with Nafisa, Fatima, and Jarif, for that selection, that's a new selection. And for that selection, again, you have P33 permutations within that selection. So first, you have C and R ways to select the R objects. And then for each and every one of these choices, you have PRR ways to count the permutation within the R selection. So basically, the process of counting R permutations from n distinct objects can be broken down into 2 tasks, and the total number of R permutations from n distinct objects can be represented as the product of the number of ways to do each of these tasks. That is CNR multiplied by PRR. So far, is it clear with everyone? If there are any confusion or question, please go ahead and ask. So far, the fact that we can calculate PNR from CNR and PRR, the product of these two. The count of R permutations from n distinct objects is equivalent to the product of the number of ways to select R objects, which is CNR, and the number of ways to count the many different arrangements within that R selection, which is PRR, the product of these two. Is this part clear with everyone?
Miss, a bit.
Okay. All right.
Please give some examples, because examples help a lot.
Yeah, so yeah, we already used this example, remember? So yeah, okay, I'll go back to that same example. But before that, do you understand that the first task of choosing the R objects can be done in CNR ways? That part, do you understand clearly?
Yes, miss.
Then after selecting R elements, after selecting R objects, within those R selections, you will also have to count all the different arrangements within that R selection, and that can be done. The second task can be done in PRR ways. Is this part clear?
Yes, miss.
If these two parts are clear, tale to hoiloi. So think about it. A duta task, and the first task can be done in CNR ways, the second task can be done in PRR ways. If this is clear to you, in that case, think about this example, specifically this one. All right. So again, the first task, think about the first task. Selecting 3 people. All right. How many ways are there to select 3 people? Just selecting 3 people from these 100 people. There are 103 ways to do that. Yeah. And then what is the next task you do? Within these 3 people, within the same selection, you keep changing the order to come up with a new permutation, and you count all different arrangements within the same selection, right? So far, is everyone with me?
Yes, miss.
Okay, good. So in that case, the first task can be done in 100C3 ways, and the second task can be done with what? P33 ways, right?
Yes, miss.
P3 ways, right? Okay. So now think about each and every selection. For every single selection that you get, every single outcome that you have in 100C3, for every one of them you have P33. That is, let's say, what is one possible selection? One possible selection is saying that Nafisa, Jarif, and Fahim are the winners. That is one selection. Selecting Nafisa, Jarif, and Fahim. That is one selection, right?
Yes, miss.
So for this specific selection, how many outcomes are there? P33. There are 3 people, and there are 3 positions to give away, where order matters. So there are P33 possible outcomes among these 3 people, Nafisa, Jarif, and Fahim. Okay, does that make sense, Arshad?
Yes, miss.
What if now I go with a new selection? What about the rest of the selection? That's what I'm saying. This is one selection, but what about the rest of the selection? What if I say that instead of this selection, I will go with Nafisa, Jarif, and Arshad? If I go with these 3 selections, Nafisa, Jarif, and Arshad, if that is the selection that I make, within this selection, how many permutations are there? How many outcomes are there within these 3 selections? Again,
PRR. Yes, miss.
Again, P33, right?
Yes,
So
miss.
you see, in total, we have C100,3 selections to make. There are C103 possible selections. And for every single selection, every single possible choice, whichever choice you make, for every one of them, you have P33 options. Sorry, you have P33 outcomes for every single selection.
Yes,
So,
miss. It's like
the
first we are just selecting the objects, then we are seeing the combinations of those objects.
We're seeing the not the combination terms.
Order.
In mathematics,
We are
yeah, the
changing
order.
the orders. Yes.
Order, yeah, exactly. In mathematics, remember, combination means that order doesn't matter. So yeah, so we are selecting 3 people and then we are counting all the different arrangements within them, and that can be done with every single selection, right? Total koto different way selection ta kora jay. The total number of different ways to make the selection is C103, and for each and every one of these selections you have P33 outcomes for every one of them. Okay, does that make sense?
Yes, miss.
So finally, in total, how many possible ways are there to select the 3 winners? How many possible ways are there? C 103 or 100C3, 100C3 multiplied with 3P3. All right?
Yes.
Because for every one of those choices, you have P33. So প্রত্যেকটার জন্য যদি থাকে তাহলে তো 100C3 এর সাথে multiply করতে হবে. For every one of them, you have P33. So it's going to be the product, right?
Yes, miss.
For the first choice, you have P33, multiplied with the second choice, you have P33, the third choice, you have P33, and so on. So 100C3 multiplied by P33. For each one of the ways to do the first task, you have P33 ways to do the second task. Is that clear now?
Yes, miss.
So for the generic case as well, P and R, if you want to count R permutations from n distinct objects, there as well, it's the same thing. It's the same idea. Counting R permutations from n distinct objects. First, you are selecting R objects, which can be done in CNR ways. And for every single one of these choices, you are counting the different arrangements within the R selections, which can be done in PRR ways. For every one of these choices, you have PRR ways to select different arrangements within those R objects. So the total number of R permutations from n distinct objects would be the product of the two. Now, again, any questions left until here, until this point?
No, miss.
Okay. Is everyone with me so far? Does everybody get it that P and R, to calculate that, we can use the product of these two?
Yes, ma'am.
Okay. All right then. So in that case, if that is what we get, isn't it possible from here to calculate CNR? We are trying to come up with a formula for CNR, right? It's possible to do that from here. Why? Because we already know how to calculate PNR, don't we? What is PNR, guys? What is PNR?
N factorial by n minus 1, n minus r factorial.
Exactly. N factorial by n minus r factorial is PNR. What is PRR?
Only r factorial.
Only r factorial. Exactly. So you already know this. From here, we can easily calculate CNR or find a formula for CNR. CNR is equivalent to PNR divided by PRR. So n factorial divided by n minus r factorial multiplied with r factorial. All right. So that's how we come up with the formula for CNR. Make sense?
Yes, ma'am.
Okay. So here again, what I want you guys to understand is not necessarily the solution itself, but the process of how we got to the solution. Because in the exam, you might be asked to prove some random thing. How would you do that in terms of permutation, combination, and everything that we've studied so far in counting, basically? If based on the basics of counting, if you're asked to prove something, how would you do that? All right. So you have to think about whether combination, the ideas of combinations are applicable here, whether the ideas of permutations are applicable here, whether the sum rule is applicable here, whether the product rule is applicable here. You have to think from those perspectives, all right? Break it down in such a manner. So the more important thing is understanding the process of proving this whole thing, okay? How did we prove it? Using the ideas of combination, permutation, and the product rule, okay? All right. So some of the things that I want you guys to remember regarding combination. NCR is equivalent to NCN minus R. Why is that? Here in this formula, instead of CNR, if you calculated CNN minus R, what would you get? You would have to replace the R with N minus R, right? You'd only have to replace the R's with N minus R, right? N would remain the same. N factorial would be here. Here, in N minus R, which one would change? Only R, right? Instead of N minus R, what would you have? R would be replaced by who? for Cn n minus r. If you want to calculate Cn n minus r or Nc n minus r, instead of r, what will we put here, guys?
Miss
N
N
minus
minus R.
N minus r, exactly. So we get n minus what? We have n here, then a minus, and then instead of r, we have n minus r, right? That's what you said. So it's basically n minus n plus r. So n get cancelled out. This one gives us r factorial. And then next we have r factorial. R factorial will be replaced by what?
N minus R.
N minus r factorial. So ultimately you get the same result. N factorial divided by r factorial multiplied by n minus r factorial. It's the same thing as this one, right? So as you can see, in case of combination, when it comes to combination, NCR is equivalent to NCN minus R, which makes sense because it's combination, order doesn't matter. So NCR is equivalent to NCN minus R. Okay. Also, the number of subsets that contain R elements, the total number of subsets where each subset contains R elements of a set that has n number of elements is NCR. If you have a certain set S where there are n elements in total number of subsets of this set where each subset contains R element would be NCR. And it makes sense, right? How do we form a subset? We just simply select elements from the parent set, right? How would you form a subset of the set S? You would just simply select elements from what? From where? From
S.
the elements of S. You have n elements in total in S. From these n choices, you select certain elements to form the subset. And how many elements do you select? You select R elements. Why? Because the subsets will have R elements, each of them. So you're selecting R elements from a choice of n elements where order doesn't matter. Why doesn't order matter here? Guys, can you tell me? Why wouldn't order matter here?
Because
Select.
selections.
Yeah, we are making selections, but why doesn't order matter here? You know this already. We have discussed set theory extensively. You've given a quiz on set theory.
Miss set
What
it
are said?
unordered. Miss set it to unordered, right?
Exactly. That is the reason. In case of set, order doesn't matter. So when we are counting the total number of subsets that contain R elements of a set that has n elements, what are we doing? We are basically choosing R elements from n options. Okay, we have a total n options of elements, and from there we're choosing R elements. All possible selections where order doesn't matter since it's sets. So in total, R selection from n distinct objects, right? So NCR. Okay, the number of bit strings of length n containing exactly R ones is NCR as well. It makes sense because we established in the previous session multiple times that there is a direct correlation between counting subsets and counting the number of bit strings. We've established that over and over again. So from that sense as well, it gives us the idea that, okay, if it's NCR for counting the subsets with R elements, it should be NCR for counting bit strings as well. However, intuition diye to hobe na. We have to find out how we get here, all right? How is it that number of bit strings? First of all, always remember this because you will apply you'll apply this concept many times over and over again in solving problems. In fact, even when we move on to the advanced problem, right at the start that you will see that we are applying this concept. The fact that the total number of bit strings of length n containing exactly R number of ones is NCR. So this concept will always use that over and over again. All of these concepts basically. So now, how does it work? How do we get NCR here? Think about it. The length of the bit string is n, means what? There are total n bit strings. Sorry, n bits in this bit string, right? Bit string and length n mane ki? It means that the total number of bit strings, the total number of bits, 0 or 1. This bit string has a total number of n bits, right?
Yes, miss.
Yes, miss.
Basically, there are n positions in this bit string, right?
Yes,
N number of bits ase mane ki? N number of positions are there. Each position will be either taken by a 0 or a 1, right? With
Yes.
me so far? Okay. And also, the bit string, each of those bit strings contain exactly R ones, exactly R number of ones. Total number of ones in each of these bit strings would be R. Exactly R number of ones in each of these bit strings. Okay. So let's look at an example, since usually that is more relatable, as you guys have already suggested. Let's say that n is equal to 5 and R is equal to 2. Right? In that case, how many bits will you have in this bit string?
It's 5 bits.
5 bits. That is, we have 5 positions. And how many ones should be there in all
2.
of these bit strings? 2. All right. So let's see what are the possible bit strings that we get here. One possibility is what? 11000. Anything else, guys?
Is 00011.
Yes.
01010.
Yes.
10100.
Okay. Like that, right? And many such bit strings like
Yes.
that. But we understand the way we are constructing the bit strings, right? We understand the idea. এরকম আরো bit strings থাকবে, obviously. But do we understand the idea? What's going on here? That there will be 2 ones and total 5 bits. And exactly 2 ones, by the way, not more, not less. Do we understand this idea, guys? Everyone?
Yes, miss.
Okay.
Yes, miss.
Now see what we are actually doing here. We have 5 positions. In the first bit string, we have chosen the first 2 positions for 1. For the second bit string, again, we have 5 positions. From those 5 positions, we have chosen the last 2 positions, position 4 and 5 for 1. Here, again, we have 5 positions and we have chosen position 2 and position 4 for 1. So every time you're actually doing what? You're selecting a certain position. You have 5 positions in total and you're selecting 2 positions out of those 5. Every new combination of these 2 positions from the 5 choices give you a new bit string. Gives you a new bit string, right? See, every time you're constructing a bit string, what are you doing basically? Every time you're constructing a bit string, basically in all of them you have 5 positions. In those 5 positions, for the first one, you chose the first 2 position 1, 2. In the second one, you chose the last 2 positions. In the third one, you chose position 2 and position 4. In the fourth one, the first position and the third position gave us a bit string. And then the first position, choosing the first position and the 5th position gives us a new bit string. So every time we are creating a bit string based on these rules, what we are doing is essentially from a choice of 5 positions, we are selecting 2 positions, are we not?
Yes, miss.
So basically, we have 5 distinct positions, and from there, we have to select 2 positions. Position 1, 2, 3, 4, 5. চিন্তা করো একটা set, and the distinct elements of this set are position 1, then position 2, position 3, position 4, position 5. What are you doing? From these elements, you're choosing 2. You're choosing any 2 from these elements, right? That is what we are doing, right? আমাদের কাছে 5টা element আছে, 5টা object আছে। 5টা object হচ্ছে position 1, position 2, position 3, position 4 and position 5. From these 5 objects, we are selecting 2 objects. Isn't that what we are doing? Does it make sense?
Yes,
We're
miss.
simply selecting 2 positions.
Yes,
So
miss.
basically, from 5 objects, you're selecting 2 objects. So what is that? 5C2. So do you see now that for a bit string, which has the length n, there will be n bits a bit string of length n has n number of bits. That is, there are n number of positions there. Okay? And the total number of bit strings of length n containing exactly R1s. The total number of bit strings of length n containing exactly R1s. How do we count that? We count every bit string where the R number of ones are placed in different positions, right? How do you come up with a new bit string? The number of ones is fixed, exactly R. If the number of ones is fixed, the number of 0 is also fixed, right, guys? Think about it. Exactly R1s, not more, not less. What will be the number of zeros?
Miss 3.
For the generic case, what will be the number of 0?
Miss n minus r.
Exactly, n minus r. So the number of ones is fixed at r, the number of zeros is fixed at n minus r. So the only way we can get different bit string is by placing the ones in different positions. So basically, we have total n bits in this bit string of length n. That is, there are total n positions, and we select r positions among these. So among these total number of n position, we are selecting r distant positions. So it's NC3, so NCR. Okay. And just like we know for combination, NCR is equivalent to NC n minus r. Here as well, 5C2 will be equivalent to what? 5C3. Because that's another way of looking at it. Instead of focusing on the ones, if you focused on the if you focused on the 0, instead of focusing on 1, if you focused on the zeros, then what are you doing? You're basically placing the zeros in different positions. So in that case, you're choosing 3 positions from the available 5 positions, right? So in that case, you have 5C3, which is the same thing as 5C2. Make sense, guys?
Yes, miss.
Miss,
Yes.
Miss, এটা কি normally counting এর মতো করে কি বের করা যায় যে how many positions are there, like we can fill without using combination?
We are using combination here. I don't understand your question. I'm sorry.
This is just normal counting দিয়ে কি আমরা বের করতে পারবো কতগুলো like positions আমরা fill করতে পারবো?
Normal counting দিয়ে বলতে কি মানে you'll come up with all possible combinations and then count them. What do you
Yes.
mean by that? Could you clarify? You'd come up with all possible combinations and count them. What if your n is 100 and r is 50? How many times are you how are you going to do that? It will take you forever.
Yes, miss.
Is that what you're saying?
No, miss, like first এ যাও counting যেভাবে করেছিলাম আমরা যে first position এ what are my choices ওইভাবে
ওভাবে করলে doesn't it make it more complicated? Think about it. It makes it more complicated, right? Because for the first position, if you think about the first position, you have 1 and 0, both options. For the second position, you have 1 and 0, both options. They simply said that exactly 2 ones থাকতে হবে, all right? কোথায় দুটা 1 থাকতে হবে এটা তো বলে নাই. So the first option, you have both 1 and 0, both of those options. If you select 1, then again for the second option, second position, you have both 1 and 0 options. Again, if you select 1, then for the rest of them, you only have 0, 0, 0 to select. How will you do that? It makes it more complicated. What you are saying. In that way, yeah, sure, there is a method to do that as well. That's another way. But doesn't that make it more complicated? Why? Because in this case, how many options you have for every single position depends on what you chose for the previous position, right?
Yes, miss.
So it makes it more complicated. In the previous scenario, এইসব জায়গায় খুব simply আমরা count মানে ওই যে product rule. I think what you were going for was product rule. Simply product rule can apply করতে পারছি না.
Yes, miss.
So এইসব জায়গায় product rule directly apply করতে পেরেছি. Why? Because no matter which one you pick in these CNR options, a CNR selection, CNR possible choices এর মধ্যে, whichever selection you go with, you will always have PRR permutations within those. All right. So here, however, it's not like that. Here, you cannot say that for every single position you have 2 options. You cannot say that. But at the same time, you cannot say that a specific position has only 1 option. It depends on what you chose in the previous position. Previous position 0 choose করেছেন or 1 choose করেছেন, it depends on that. So if you go by that approach, that makes it more complicated. However, if you think of it in terms of positions, তাহলে basically কি পাঁচটা পজিশন আছে পাঁচটা পজিশন আছে 1 2 3 4 5 এই পাঁচটা পজিশনের মধ্যে আমার জাস্ট দুটাকে সিলেক্ট করতে হবে, any two has to be selected. So what is that? 5 objects, 2 objects to select, so NC2, 5C2. All right, and if you think about 0, then 5 positions, you have to select 3 positions, 5C3, which is the same thing. Make sense?
Yes, miss.
All right then. Anybody has any questions left regarding this explanation? Please understand this, because we will use this concept right at the start of the next session in the next week. Okay, so now let's do an example for combination. Here again, the key part is identifying the fact that you have to apply combination here and the product rule. All right, the most important thing is identifying that combination. You have to apply combination and product rule here. Why? Because in discrete mathematics, that's what we do, right? We try to find similarities between problems that seem different at the first glance. And how will that help us? If we find similarities, then we can solve different problems in the same way. All right, we can solve problems which seem different in the same way. All right, so in order to be able to do that, you have to first be able to identify that, okay, this problem falls under the combination and product rule category. Okay, how do we know that? Let's go over the problem. So the task is basically to create a committee where there are 3 members from the maths department and 4 members from the CSE department. The maths department has 9 members, 9 faculty members in total. The CSE department has 11 faculty members in total. And in order to construct the committee, you must select 3 members from the maths department and 4 from the computer science department. Okay. And mainly our task is to find out how many ways are there to create this committee. How many ways are there to select the members of this committee? How many ways are there? If you think about the number of ways to select the members of this committee, then the process of creating this committee can be broken down into 2 tasks. The procedure of creating this committee can be broken down into 2 tasks. The first task is selecting the 3 faculty members from the maths department, and the second task is selecting the 4 members from the CSE department. Is everyone with me so far?
Yes, miss.
So we broke down the procedure into these 2 tasks. Now let's see how many ways are there to do each of these tasks. The first task, which is selecting the 3 members from the maths department, for that task, how many options do we have? Think about it. We have to select 3 members from the maths department, right? We have to select 3 members from the maths department. But how many members are there in total from the maths department?
9.
9. Correct. There are 9 members in total, and from those 9 members, we have to select 3 members. Now, this is a committee, right? This is a committee. So you select 3 members and you're done. It doesn't matter in which order you select the members, right? Because this is a committee.
Yes,
If you select 3 members, then that is one selection. If you select the same 3 members in a different order, will that give you a different committee? No. Since this is a committee, you only have to care about selecting 3 members out of these 9 faculty members. All right, just selection. That's all you have to care about. Because if you select the members in different orders, it doesn't make any difference because it's a committee. All right. So choosing 3 faculty members is just the task of selecting 3 from 9. So you have 9 distinct objects. Since they're faculty members, you can assume that there are 9 distinct objects. So you have 9 distinct elements. From those 9 distinct objects, you're selecting 3. And a matter of simple selection. Order doesn't matter. So how many ways are there to select these 3 faculty members from these 9 members in total?
Miss 9C3.
9C3, exactly. So there are 9C3 ways to do the first task. What is the second task? Selecting 4 members from the maths department. How many? selecting 4 members from the CSE department. Sorry, selecting 4 members from the CSE department. How many members are there in total in the CSE department?
11.
11.
Then it is 11C3. It's 11C4.
11C4, exactly, 11C4. Now, next, now that we figure out that it's going to be NC3 and 11C4, is everybody clear on this, that the first task can be done in NC3 ways and the second task in 11C4 ways? Is everybody clear on this?
Yes, miss.
Okay. In that case, the first task, which can be done in NC3 ways, for every single choice of the faculty member, every single selection, for every single choice of selecting the faculty members for the first task, you have 11C4 ways to select members from the maths department, right? For every one of those selections. There are 9C3 ways in total. There are 9C3 choices in total. 9C3 choices in total to do the first task. 9C3 ways to do the first task, which is selecting the 3 members from the maths department. For every single selection, J selection take karo, for every one of those selections, you have 11C4 ways to do the second task, which is choosing members from the computer science department. Since they're related like that, we can apply the product rule here. Think about it. From the maths department, let's say you choose faculty member A, faculty member B, faculty member C, okay? Once you've made that choice, from the CSE department, how many options do you have? 11C4, right?
Yes, miss.
So that's one outcome, the selection that you made, faculty A, B, C, and then 11C4. For ABC, with all of those choices, 11C4, ABC সাথে 11C4 থেকে যে যাকেই পিক করো না কেন, কম্পিউটার CSE ডিপার্টমেন্ট থেকে যে 4 জনকেই পিক করো না কেন, every one of those 11C4 combined with this ABC choice gives you a different outcome, right? And then if you go with a different selection from the maths department, let's say you go with BCD, faculty member B, C, and D. For that selection as well, again, you have 11C4 options. 11C4, I shouldn't say options, 11C4 possibilities to select 4 members from the CSE department. So for every one of the choices that you have here, for every one of the choices of the committee members from the maths department, you have 11C4 choices to choose the members from the computer science department. So NC3 multiplied with 11C4. Does that make sense, guys, to everyone?
Yes, miss.
Yes, ma'am.
Both parts. We are applying combination here for each task and then the product rule. The application of combination and product rule. Both of these. Is it clear with everyone? Are there any questions or confusion left?
No, miss.
Clear, Fahim?
No, ma'am.
Yes, miss.
Okay, very good then.
Miss,
that's it.
if there were ranking, like we have to choose 3 members, but there are rankings, then we were gonna use permutations, right?
Exactly. Very good. Yeah. Very good example. Yeah. Instead of this, let's say they said that you have to choose the president and the vice president and the treasurer of this committee. In that case, suddenly it's different, right? Because the positions have been specified. They're designated positions. So in that case, we wouldn't be able to use combination there, because in that case, order would have mattered, right? Okay.
Yes, miss.
All right. So any questions left regarding this session?
No, miss.
All right. In that case, I can stop the